Hi there, this is KOJRO, and this is the start of what will be my third episode in the 100 watt amplifier series, and I do struggle a bit. I have been wanting to test this now for a couple of days, but I've actually struggled to find some of the documentation I really would expect to find about this somewhere on the internet. They claim that this is a famous design, and some of it is. Some of it I've seen some copies and I've seen some recreations and stuff, but I actually can't find the original source of this design. And even though I have a schematics, it's not very accurate. I will show you in a bit some of the inaccuracies that I found, and what I'm really looking for is something that I will give a brief explanation of shortly, and that is the term bias that you have in an amplifier. If you have a real class A amplifier where the whole sine wave is done in one single transistor on the output, the bias will be 50%. If you have, or more actually, if you have an AB amplifier, you do have some bias to compensate for the crossover between where one transistor takes the positive part and one transistor takes the negative part of the signal, to have the whole span of the output from plus 35 to minus 35 volt. So this area where one transistor takes over for another one, that is where you need the bias. So you need to increase the bias to make the curves overlap as best as they can for the transistors. I will try to show you this in a presentation just after this, but I do have some problem with this, because they say that if you have too much bias on this kind of CMOS transistors that is really meant for switching on and off, you will have something they call a thermal runaway, and that is because these transistors is not increasing their resistance on the input when they are getting hot. So at some point they will get so hot that this circuit will go into oscillation, because it will increase the amplification on the circuit. And there is no real thermal compensation on this, of course. Some of these components are kind of activating the thermal characteristics, so they will prevent this, but I don't think it's enough. And they say that you should decrease the bias so that they will not get so hot. And of course, the bias is all wasted current, so the more bias, the more hot it will get. And the more hot it will get, the more likely it is for it to go into oscillation because of thermal feedback. So I've been looking for an answer. What is the ideal bias on this, and how do I measure it best? And that's not easy information to find. I have found everything from 20 to 150 milliamps, and some even say 200 milliamps, but 200 milliamps on an amp with just a single pair of CMOS transistors on the output, that's really much. You can get some really good toasty room heaters with that much current into this amplifier. So that's what I will be doing this video. I'm not sure if we will going to be able to do the actual test. I will first run into some of the problems I ran into in the schematics and try to find some explanations for things there. And I also will show you some of the information I found when I was digging on the internet to reveal some information about this. So I will get on to that just of now, and hopefully I will be able to test this before I move out of the garage as my temporary workspace. So, as you can see in the back, I'm dragging a lot of stuff with me, so I will need to clean out this space so that the dog will get his home back. But for this episode, I will stay firmly planted here, and hopefully I will be able to connect this to power if I can get enough information. So let's crack on. Yeah, this is the original schematics from the Aliexpress webpage, and I have some questions about these schematics, and one of them is these resistors here. They are in my case, I have put 10 ohm resistors here. They actually was missing from my kit, but when I look onto the pictures from the internet, they are put in here with 10 ohm resistors, and they have, yeah, I have not seen a construction where they have not used a 1/4 watt resistors, and they are in series with the plus. I actually have 38 or something, and minus 38 down here, but they are in series with everything that is drawing current behind this point here. So everything here, the currents that goes through these junctions here, they pass through these resistors. So I was going to check what is the maximum current you actually can draw from this when you do have a 1/4 watt resistor. So that's what I set out to find out. And here is my trusty old, what can I say, this is Ohm's law put into a system. I kind of like this model here because it's instantly tell me, and I'm not using this every day, so I get off track. I do remember the old sayings from back in school. V are equals R times E, URI, and I also remember PUI for power is voltage times current. But this is my my cheat sheet on this. Just to point out what we have here, I'm using this formula here for determining the maximum current, and I take a 1/4 watt and it's 10 ohms, and that gives me 160 milliamps. And of course, with a 1/2 watt resistor, I don't get twice as much as this, but 220, 230-ish something. Easy head. I'm not doing this every day, but my head is telling me that about. And the maximum voltage drop that we will have over these with the maximum power that these can dissipate is about 1.6 volt. And that is not much. And they are in series with quite a lot of stuff here that will have current pass through each of these networks. So is this sufficient? I'm not totally sure about that. And I also have some other questions. And in my circuit, I do have these two capacitors, and I couldn't find them in the schematics. And I measured out where they are, and they are placed here. They are probably there to take parasitic noise on the input because they stand between the base and the collector and is short-circuiting high frequency up to the collector so they don't enter the base and is amplified. And it's the same down here. So one is on the BD140 for the positive part of the signal, and one is down here on the BD139 for the negative part of the signal. So I have placed them in the schematics, and I also have some other questions, and it is these circuits down here. You actually have two filter circuits here. The first one is this, and this is a parallel circuit with a resistor and capacitor, And on low frequency, it's just the resistor that will be active because the capacitor will have a very high resistance. But with higher frequency, this will shortcut more and more of the signal just to ground. So it's a typical low-pass circuit. And this kind of filter, it's determined with the frequency where it reaches a -3 decibel curve on this. And that is we call it the FC. And it's the formula for this is 1/2 PRC. And in our case, we have a 20K resistor and we have a 330 picofarad, that's 10 in -12. And that gives us they start to cut off this frequency by 24 kilohertz. And I would like this to be higher for this to be a real hi-fi instrument. Of course, my old ears doesn't hear anything about probably 15, 16 kilohertz is the absolute maximum. So this might be good enough, but normally in hi-fi amplifiers, we have the cutoff frequency much higher than this. This other guy here, it's a 3.3 microfarad capacitor and a 680 ohm resistor. This is really a very low resistance to have in these kind of circuits. You do, in addition to this resistance, this actually will look like, I can draw it down here. You do have a capacitor here, and you have the first resistor, that is this one, R1. And then you have the resistor equivalent that you are running through down here before this goes to ground. And that is the resistance you have in this junction, you have in this transistor, you have in this junction, this, and also down here. So this will be almost neglectable in this circuit. So this will have a very, very low frequency. I think this will, almost to DC. So this main reason for this being here is to avoid having DC bias in here. Because if you connect this to a circuit with maybe a 10 volt with no AC coupling here, you will have a bias on this resistor that will be quite high. So that is the functions for the input filters and stuff. And this is normally not that high as 3.3 microfarad. And as we established, this is an electrolytic capacitor, a bipolar of the kind. So I'm not very happy to have that either in the signal path, but it's there and we are going to test with it in the circuit. And I actually redraw the schematics because I did have some more questions about this schematic, so I just draw it up again and put on some new values. And I also was looking for missing values, so I made a new component list. C7 was not named at all, so I just used the C7 name again on a new capacitor. And this C12 was not named at all. C7 is the input I put there. And C13, it's this one here. It was named C22 for some reason. And I also had these 100 picofarads that we drew in last time. They was not in the schematics at all, so I just called them C14 and C15, and it's these ones here. And I also put everything else in here, and I made this component list. This is nice to have if I want to do some fault finding or other stuff. And I was looking to find out what in the world were these A's. And I figured it out. It actually is a connection here. So these are connected together. So this actually is not a test point as I thought it was. I wasn't seeing this at the first time, so I was only looking to the one on the output and take A, okay, maybe a test point, but it's the same point as the speaker out. So I didn't understand this at first, but when I redraw the schematics, I saw that this and this was some junction point. So in the real world, they are connected together, and I measured this out. They are connected together, so I just misunderstood the schematics. And what about measuring the BIOS? Normally, when you measure BIOS and an amplifier, you short circuit the input to avoid noise, and you measure on some of the components that the current goes through. And on one transistor output, no transistors in parallel, you normally just measure on this resistor here, and you just calculate how much voltage you should have over this resistor to have the bias current you want through these resistors. And I've been speaking about bias, and I'm going to show you just real quick what a bias is when we are talking about amplifiers. An A-class transistor is normally single-ended. It does have just one transistor. But in AB transistor, AB amplifier, you do have two transistors that is overlapping with the amplification. And you have a curve that looks like some part of a hill. And I've tried to draw this up here. When you have a positive sign here, this transistor here is on and you get this one. When you have the negative input here, this transistor here is on and you will have this negative wave down here. But if you take into account that this is not a linear circuit, and actually these are quite linear, they are almost totally straight from, not even that point, it's from this point to forever probably. And you do have the same with the other one here. They do have a curve that is straight, but they are not totally the same. So I'm not sure if this curve that you normally draw like so, and this is where you use the bias to make sure that you are not using this part of the transistor curve. So you are having a small current run through here so that you are lifting and lowering the part of the transistors that is used to amplify the signal. But this is very steep and you do have a bias here. So if you was not using them at all for this, you would have one curve that goes like so, and this is actually drawn the other way around. So it will, it does not go upwards here, but you get the gist. And what we are using so that we are not using this part of the signal, we are using this part, and we kind of move them together with the bias. And then they will have a curve that looks something like this, with this is minimal. This was not a good explanation, but I can just show you what the result will be. If you eliminate this part of the curve, you will have some slightly distortion down here, but the more you use just this part of the curve, the less this will be, and the more you make sure that these are not overlapping but continuing straight, the less distortion you will have. And this is called crossover distortion, and it's when you're changing from a negative to a positive signal. And the key point with a MosFet transistor is that it's very, very low input current that goes there. So a very small voltage or a voltage is driving a huge current on the output. Just take this out. The difference here and here on this curve, where you will have a very large power draw, this is a logarithmic scale. Yeah, that the scale is logarithmic is of course making it very difficult to show this, but here there is a huge current steered by a voltage swing, and the voltage swing is swinging into a high impedance input on a MosFet, so that it's almost no current in the amplification process or the input stage. Our amplifier is a mix between bipolar and FET transistors. And the circuit in front of here is bipolar in its nature, so there will go some current also here. But the output stage is mostly voltage driven, so a small change in voltage or the change in voltage that you have here will trigger the current on the output that is manifesting itself with a voltage drop here that will make this swing. So I hope this clarified things a bit. If I'm not good at explaining this, at least you can see on the curves what I'm talking about. So that's it, and now I'm going to show you some of the finds I did, what I found in the internet when I tried to find out actually how much current is going through this to make this a good bias. I can of course look in the schematics, I can test this, I can look in a oscilloscope, but I don't have my oscilloscope here, and I don't have my waveform generator, and I only have one multimeter, my Fluke here. So let's see what we find on the internet about this. In my search to find out more information about this amplifier design, I browsed through this webpage, Transonics Pro, and they have the same amplifier board. They use the TO3 versions of these transistors, but otherwise they look all the same. And it's about the same schematics. They don't have the capacitors here on the base of the BD 140 and 139 down here. I'm not sure, maybe you are not seeing my pointer? No, you are. Okay, they don't have the capacitor here on the BD 140 and 139. And he don't tell where this amplifier design come from. You do have some information about the transistors and some other stuff down here. But it's not very useful for me what's here. We also have some close-ups where you can see this design. But it's basically the same, and it's basically the same schematics, and you do have about the same set of everything. I do think it's almost exactly the same. You don't have the extra electrolytic capacitor up here. There is a 1000 micro capacitor that is missing in this area here. And this is 10 picofarad. 3.3, this is 10 ohms, no, otherwise. And he also has done something here and made a sketch of a power supply, and he has made a power supply for the 50 volt DC, where he is using a 35 volt 8 ampere transformer, and he has used 3 times 4700 microfarad, so he has somewhat similar capacity on his capacitors than I have. And I also browsed through this guy, and this is a page that is in Russian. It's komitart.ru, and I don't understand Russian. I can some, but not much. But this looks like the exact same board that I have. I do even think that it's almost exactly the same. The silk screen is a bit different, but that's all. He has said that this is 100 micro 63 volt instead of 50 that is on mine. And he has done some work with these schematics. He has seen the same shortcomings I have with the numbering of the components and so on. And he has also identified that these capacitor here was missing, so he has included them in his schematics, both here, and it's also an updated design with a 1000 microfarad capacitor here. So had I found this schematic first, I would have known about this and I didn't have to reverse engineer anything. Otherwise, it's about the same, I think. And he also has some other interesting information. He says that if you are going to use 4 ohm, then you can supply it with as low as 25 volts. And if you are going to use this with 8 ohms, he says that you should have 35 to 55 volts. And that might be because of the bias and so on. And he also do say something about that you should measure the bias to be from 5 to 35 millivolts minimum, and from 30 to 170 milliamps ideally. I do think that 170 milliamps, that's way too much, but I'm not totally clear. I've tried to do some translation of this, but yeah, I can show you afterwards what Google Translate tells me about this. I also got a Russian-speaking person to look into this, but it was too technical. And he also states something other interesting that I have asked some questions about earlier, and that is this R17 and R18 is his numbers on this. The 10 ohm resistors that stands here in series with the power input to the voltage amplifier stage, that is the one in front here. And he stated that this should be half watt. Mine is only, it's these resistors that's here on this PCB. My resistors here is only a quarter of a watt. Was there something else interesting here? I don't think so. I think, and he also has done something other very interesting that I really wish that I would have thought about, and that is he has soldered the transistors on the back, the flip side of the PCB, and just have to bend them once. And that is actually a marvelous idea, because then you will lift the PCB and you will be able to put the heatsink under the whole PCB if you want. And you can place this straight through to a heatsink or a plate with something. So this is actually a really good idea. I wish I would have thought about it before I bent all the legs on the transistors. I don't think they will stand to be taken, straightened out and bent again. I think the legs will break. Yeah, and it's also the schematics here it's doing something with the numbers, so it's not totally the same with the numbers as the original. He has named this capacitor C7, so he has named everything from left to right when it comes to numbers, not taking this in turns and gone back and forth as the other guys have done. So we have learned something. We do have a mention down here about that it's actually will work with 25 volt, and they also say that 30 to 170 milliamp bias. And I can show you now what the translation looks like. It's not very good. And here you can see the Google Translate document. This is actually the link to the web page. And this is just gibberish. And that is because I couldn't cut and paste from this web page, so I had to do some trickery to get this cut and paste. But we do have some working voltage at work on load 8 ohms. And he also stated here that he has discovered the extra 100 picofarad capacitors. And he tells us something about adjusting the 1K, 102 resistor. And he also says that he has tried this with a bias at 30 milliamp to 170 milliamps. I'm not sure that is a good idea, but we will look into that. And oh yeah, 5 to 30 millivolts. That is because he is measuring the 30 to 170 milliamps over the 0.22 ohms resistors that is standing in series with the signal when it's going to the speakers. So that is the normal way to measure the bias, and he says that it should be in the range of 5 to 30 millivolts. Yeah, but what do we have here? If we have 5 millivolts and divide that by 0.22 ohms, that's 22 milliamps about. And with 0.03 volt or 30 millivolt, then we have 136 milliamps. So it's not the 30 to 107 milliamps, but we are in some margins here. So I think that's okay to measure in that range. Let's see if there is something more to learn from this. We can go through the component list. He is actually using the 4.7 ohm and not the 10 ohm resistor on the output that we discussed in the previous part. And he has said here that these resistors should be half watt. I might just change them with several more resistors and take out the 10 ohms, but they will probably just burn and make a short, so I leave them in there for now. Yeah, otherwise it's nothing interesting here. I did get to know some things. Yes, we have to get further with this project, and I started now with a long piece of aluminium that was like so, and since I'm still stuck in my garage, I hacked this up with my I don't know what this is called in English, but this is actually a Sandvik 226, and this is an iron saw, and it uses these blades. And I've had this for many years, and it's starting to get a bit bent because sometimes I take the blade and make it far too, I put too much strain on it. It's this built-in lever here on the back. And when I'm making this really tight, it's much straighter cut. So I cut 2 pieces, and this is some massive piece of aluminium. And I can tell you some things about heat sinks. This is quite the massive piece of aluminum. It's 5 millimeter thick. It's 85 by it's 15, I think. And when you are making a heatsink, of course, the mass of the heatsink, how much it will and how fast it will heat up, it depends on how much aluminum you have here. And it's quite the good heat conductor, so the heat will spread evenly throughout the material. And there are different kinds of aluminium. You do have rolled aluminium, you do have cast aluminium, and you also have some other kinds and some other mixes of aluminium. So they all behave a bit different, but mostly they are the same when it comes to cooling. But there is a lot of theory behind this with making efficient cooling. You have to know something about how heat radiates from these kind of things. And black objects gives off more heat by radiation and convection, and also if you have a lot of surface for the air to circulate by, then it will heat better. So this is not a very good, what should I say, heat spreader or heat sink. I call it heat sink. And if it has had these fins on the back, it would have been much better. I had much more surface area. The other way to go is to use a massive block of aluminum, and that is also quite good. It takes some time to heat it, and you do have some heat spread, but the surface, it was decide how fast the ambient temperature and this temperature will be the same. So what am I going to do here? I actually got these in the mail, and this is Aliexpress El Cheapo silicone rubber mats to have behind these kind of transistor packs. And these are already plastic coated, so I don't need to have any more insulation in between the screw and this. I should use some heat paste. Yeah, there is a lot of confusion about these two on the internet, so I do have to give this some notice. If you take a sheet of aluminum like this and rub it with a pen or something, you will see that there is a lot of marks and scratches in the surface. And the main purpose of the cooling paste is not that it cools by itself. It actually is a good conductor of heat, but pure aluminium is better. So why do we use this kind of compound in here? And that is that you should have as much contact as possible between this surface and this surface. So if I should couple these two heating elements together, if I use cooling paste between these two and map them together, the cooling paste will fill up the voids and make the contact area between these two materials much better. At least that's the theory. So people that is using heat spreaders, and they use this with their CPUs, and you have a CPU with this much heat spreader, and they put a small piece down here of cooling paste. That's not the way to do it. You should put it evenly on the whole surface like so. That is the purpose, because it should spread into every microscopic crack and surface impurity here, so that you will get as much of the heat from the heat spreader on the CPU transferred to the cooling element. But enough about that. Let's see what we are going to do here. In the last part we saw that it would have been a great idea to put these just on the bottom here. Then I could have just placed these like so and bent the transistors down here and just put some distance elements here and just screwed it like so, and I would have had a finished element to test. But no, I didn't do that, so I'm bound to fasten it something like so, I was thinking. And then I need some spacers on the bottom here. And I do have some sortiment box with these, and normally I use just the ones that used to follow with PC boxes back in the day. But maybe just something like this, or I can use this one and just use some 3mm nut. It doesn't matter if it's some place away from the bottom, because this sortiment like this should be so that I can mount this in some kind of fashion here. So I just think I will measure up the distance here and say that I can use spacers that is this length, and this is, it's just 10 mil, 1 centimeter. So what do I need to do beyond that? I need to drill some holes, and I do think that 3mm holes will suit me just fine. And I need to drill them so that I will be able to fasten these. And are both my boards exactly the same? Do I need to do some special drilling? I actually couldn't find my other board. Have I dropped it behind somewhere? Yeah, I have to go look for it. Or go is an exclamation. I'm Still not able to walk. But I do think that I will make this fit. So if I just measure out the distance and put this someplace in the middle and I mark where I want the holes, I will be able to continue this. But first I'm going to just screw in some distancers in this. I do think I'm just using the ones with the nuts. I just need 8 of them. It was this kind. And if I take they will stand quite a bit up from the surface here. Let's see if that matters. No, it really doesn't matter at all. It can be good to check to see if there is some conductive areas here, but they have routed the traces so that they won't conflict with this. It's a black silk screen. It's not my favorite because it's very difficult to see the traces. Yeah, so now I have that going, and I also have the possibility of just doing like so. And then I can say that if I am able to put a mark in each of these, I can just make some pointers for where this will be. And I don't have much in the way of pencils and stuff, and this one, it's too thick. So maybe I can just cheat and use my measurement leads. Maybe I'm able to see where I was scratching here. Yes, I was. It's impossible to see on the camera, of course, because I will just make some marks here. I have to check that this is about in the middle. 46 and 50. So the first thing I'm going to do is that I'm going to check how far away each of these are. Because the distances that should be here is 11 millimeters, 11.5 millimeters. 11.5 millimeters between each of these holes. If I do some paper thingy here between these, and the distance between these two, $65. And if I measure up the distance between these two, then I have to make some assumptions here, but this is a bit at least possible to change by desoldering and soldering them back in. This is 7. I can check this one also. It's 7. So I should make 2 holes with 65 distance, 3 holes here, and the distance from the bottom to this is 33 and 33. So what do I need to do? I'm going to scratch this out, and I'm going to make some marks again. This is not my best tool for this, but again, what can I do? And this should be 15. So if I take 7.5, that's the middle one. Was I that close with this? I had 47 on that one and 49, so I was just about 1 millimeter off on all these holes. then it's just easy to measure. So there, I have this line, and then I can, I will make this a bit thicker around here, because then when I scratch, I will see where the scratches are on this. Like so. And my thought was that when I have drilled this, and I don't have any good drill here either, I just have my hand drill, battery powered. I do have a smaller 12-volt piece here, so I will drill this by hand. But I will try to get something to measure this a bit better. I don't have any of my steel rulers here, I think, other than this, but we will try to get it as accurate as possible. Yeah, I'm going to use this. This is quite a pointy thing, and even though this is red, the same color as my trusty old KOJRO connectors items, this is some GV something, and I do have several of these, so I do think they are a reputed brand too, and I actually thought when I first saw this that this was a KOJRO. This is a 2-inch something, and I have this here that I can use, and just to make sure that I'm on the right track, I will just see where I am at here. And it's this one. Like so. And like so, because then I can, that is the line there, and on these here, this of course makes for terrible video footage. And this is 15, it's the middle is 7.5. That's the middle. And that means that I have that. And then it should be 11.5 out from there. And sorry, I'm already messing up things here. That is the middle. And 11.5. Is there. And it's there. And this should be 65 I wrote. And 65 parted by 2 is 3.25. So 3.25, that should mark the middle. Can that be correct? It's actually 55. So I did get this wrong. It was very good that I... 55. Then it's 27.5. It's like so. Yeah. Going to use this. This is a hammer. Picard something, number 87. And since this is really sharp and this is just aluminum, that will be enough markings to get the drill going. And I will just drill this as best as I can off camera and see how that goes. See if I have a 3mm drill bit that is sharp enough to cut through this. Aluminium is normally quite easy to drill, but it's you need a sharp drill bit because it's kind of some resistance in this because it's not as hard, so the drill bit easily break if it's stuck. Yeah, I've drilled the holes and it doesn't look half bad. Yeah, it does look half bad, but not anything worse than that. And let's see, I put these two, they are not exactly the same. These are hand saw and I have not cleaned them up in any way. But yeah, if I clamp them together, or maybe I just clamp them together and drill through these ones. I do that. So then both of them are drilled, and I've used some Scotch-Brite to just knock off the worst on the side. Yeah, I done it on both sides actually, but mostly there is one side that is not many scratches for both of this, and I'm going to just screw things to that side. So I'm going to try to fasten this on one of them. I'm going to see if I don't have any caps that fits these, but I'm going to check if I have some TO 220 silicone pads. Otherwise I can just use some scissors and cut down one of these because I have a lot, as you can see. Yeah, I lost a bunch of footage here. I did cut up 3 of these. You can see the pieces laying about here. I actually had lots and lots of these. The whole bag here, it's 100 I think. And the TO 220 I just had a few. And I just put these together. Actually, I forgot the spacer on this one. I put the spacer on that. I will take it off and put it on. Because there is one thing that we have to remember when we do this, and that is that metal is expanding when you put on some heat on it. And when metal is expanding, you will be able to crack some plastic when this is tied down really good. On the middle ones, the screws was not long enough, but I do have some longer screws, but I didn't have more than 2 of them up here, but I will find some more. You also have the rubber in between here. It also takes some of the pressure, but not much. And these screws is from the same box that I had here before, and I do have some screws. They're really long or too short, so I will find 3 more screws. I do have some goodie baggies with screws lying about. So what do I need to do now? I need to make a hook that I can connect these 2 signal wires together. I need to be able to measure over this point, to measure the current that goes into this. I must put this in the middle position, I think. It's easier to adjust that way. And I also will crank up the power. This is the positive, negative and ground. And I will connect it up to my variac transformer, so that I will be able to ramp up the voltage and probably test this with 20 volt or something, so it's a lot less current going into this. And I will just see how things work out. The goal here is at least to measure that it's maximum 0.3, wasn't it? 30 millivolts, wasn't it that? Over this this resistor to measure the bias current. And afterwards I'm going to just fix a signal wire that can go into this, and I can use my old Nokia phone that still has a 3.5-inch connector, and I do have a signal generator app on this. my signal gate generator is, I do have actually 3 of them, and one is broken, one is in the shed, and one is in the basement, and I can't reach either one of them today or tomorrow. So I'm going to continue this test tomorrow morning. It's getting very late today. It took a lot of time to cut this. My arm is still not good, so I'm going to make sure it's safe. I'm going to check everything once more, and I'm going to make everything finished to make a test. So I'm going to make the 3.5mm signal wire that I can put into that connector. I'm going just to make that up. And what else? I'm going to, this is ready, all of it, I think. The spade connectors and everything should be in place for this. So I'm just going to hook that up. And when I say everything is ready, it's of course the spaghetti that we used before. Just going to put away some tools here. Yes, and here is one output, and this is positive, and this is ground, and this is the negative. Double check, yes it is. So this should be connected okay, and these two should be shorted. Let's see if this will fit. It does. Like so, and I need something to just bend this, and I'm going to get a wire. Kind of thick, but at least it's in there. I do worry that this picture is grainy, that it's not high resolution, but I will have to see. This is what I have. And the measurement, I will just put it like so and measure over here, and I will be able to reach the screw here. Yes, I'm back here, and I do have my setup here. I do have my power connector, I do have the fuse, and I do have my Wago clamps. It goes into the transformer. The transformer circuit is like it has been. I have not connected in the Variac transformer yet. I'm just going to go over all my connections here. I've connected up the amplifier. I have my capacitor bank. Hopefully anything won't fall over. And I made this lead, and this is just some clamps. Connect them into my multimeter like so. And this is to go into the amplifier, and this for the speaker output. And this should be connected to the other side of this resistor, and that will be the transistor like so. So everything now should be connected up, and this was, we noticed that this should be maximum 0.3 volt over here, and as it stands now it's 0. I have two ways of limiting the current. I've started with about 0 volt from my Variac transformer. I should have another multimeter to measure the voltage input here. Let's see if I can get another multimeter connected here to measure the input voltage. I can see what I can get. Yeah, let's see. I'm going to try this one out. This is my 1988 model Metex. And put this on 200 volt DC. Yeah, I can just put it here. I found this El Cheapo leftover from somewhere measurement leads, and I'm just going to, I know this is symmetrical, so I can just put them, they are plugged into the plus and minus on this, so it should show the differential voltage between plus 35 or the plus and the negative power lead. And now it's measuring 21. It's some just noise. I'm going to plug in the connector. Everything is still connected, and there should be a low voltage here. We have 8 volts over the capacitors, if everything else is correct. And this should be on volt, so we should get a readout here, DC volt. See if I take this up. Is it possible to see? No, it will not be. So if you put it like so, I will be able to watch, and you will also see it on the camera. I will, oops, sorry, I moved the camera stand. Let's hope that this will stand still. Wrong way. This is still volt DC. So this is actually 1 volt. So this should be millivolt. And I don't know if I do have any, oh, there it's millivolt. Sorry, millivolt AC, millivolt DC, 3 millivolt DC, and it's minus, but that's okay, because I have not checked the polarity of how I measure over this. So that is quite okay. And let's (4.2 millivolt). I will have to get a better screwdriver, and I will try to turn the potentiometer and see what happens. It's not the best of screwdrivers, but we can use this to check what is happening when we adjust. The power is going down, the power is increasing. So the voltage is going down when I increase this. So I'm just going to turn this lever down. Very low voltage, like so, and then I'm going to increase the voltage here. (3.4 millivolt). Do you remember this was supposed to be about from 5 millivolt to 30? It was 136, I think, milliamps, when this was 10 times what it is now. So I'm just going to increase the voltage some more. Just check that this is not running wild. We do have 6, 7 millivolt. Nothing is getting hot. And it's still possible to decrease this. So 4.9 millivolt. No, it's 81. This is not sure this is correct, but it's about the same, and it's 6.4 millivolt. And if I try to increase this, and again that this is minus 11 millivolt, it doesn't matter, because it's just the differential voltage I'm measuring. Still ice cold. Well, not ice cold, it has the ambient temperature of course, but it being aluminum, it's always cold to the touch. Oh, it's 20.5 millivolts. Let's keep it there for a while. See, it's going down. There is some current going through this, but it's not very hot. I will try to increase it a bit more. Sorry for my hands being in front of the camera. Oh, you can see that the voltage is also increasing a little because there is some more current running through this. It's not starting to get hot, but I can feel that there is some current going through this. You can also see that it's gradually going down. So even though we adjust this to have about, now it's about 100 millivolts, I think, milliamps. I can make some quick calculations on that. Let's see. We take the current is the voltage divided by the resistor minus 22, 0.022 divided by 0.22. Yeah, it's about 100 milliamps that's going through this now, and now it's starting to heat up. It's been on now for about 10 minutes, and you can see the current is dropping, but we're also getting some heat here. I'm trying to get my thermometer, but it's about 65 degrees, I will guess, and I don't think it will burn with this, but I'm going to turn it off just to make it cool down, and I will start it again when I get a thermometer to follow up on this. Yeah, now you can see I turn off the power and the capacitors is draining. You can see this one, this is the draining of the total power supply. So we could have used this to measure the capacity on the capacitors to see how long time it takes them to drain with the known current. So the capacitors are fine, they are doing what they should. Yeah, now this has cooled down a bit. It's 26 degrees, 31 when it's close by, 34. Yeah, 34. And I'm not going to ramp up the temperature this time, I'm just going to turn it on. Quickly up, and the current is now a bit lower than it was when I started this. It's increasing. Last time we saw that the power was decreasing when 36. I will keep it on now for a couple of minutes. This is a bit inaccurate when it's not close by, but we just keep this heating up for about 10 minutes. Yeah, it's been left on now for about 10 minutes, and we have some problems with this because when it's tiny blank surfaces, it's not measuring totally correct, but I do have about 40 degrees on the black of these transistors. There is some wire in the way here, but 40 about on this transistor. If I take a pencil here and make this blue like so, I can check what this says. It's not measuring more than 35, 37. Let's see now. I don't get this to measure totally correct because it's not too hot to touch. If you can't hold this for more than a few seconds, then it's far too hot for this kind of work, but it's most I can measure here is about 36, and down here it's 44, so it's getting hotter, yes, definitely. 46. But of course the heatsink is doing its thing, so. But what do we do with the current that is not stable? 15.4, and of course it's good that the current is decreasing with increasing heat, and that means that it's far less chance before thing runs off. But the current should really be measured when it's in the running temperature, so I'm going to try to adjust this a bit now when it's warm and say that it should be about 20 when it's hot, and then it's going to get even hotter. Luckily it's a multi-turn potentiometer, so it's easy to get this accurate, but of course you have to turn it sometimes to get a result. Let's see what that does. 46. I always had good results with this thermometer before, and I do think it's measuring accurately, but I do think that the shiny aluminium is leading it astray a bit. Yeah, it's not killing hot. I'm going to adjust it up a bit more. With 20 millivolts, we are still a bit below the 100 milliamps, and the recommendation was up to 160, so we are still far below that, but I don't have the heatsink to take 160, that's for sure. 47, 48. Yeah, let's keep it on for a couple of more minutes. You can see it's still going down, so the temperature is still going up. Yeah, the active components like the MosFets and bipolar transistors is the only components that have a temperature coefficient that we need to take into consideration, and probably it is the driver transistors and the output transistors that is making this current go down. And we need to have this stable. You can't have that so that when an amplifier heats up, it gives out more distortion than when it's cold. I of course have one more board to test, and I'm going to mount this also up on mounting it to the aluminium. I do have the other one finished drilled here, so I'm just going to cut everything, put screws in, and I'm going to test that also. So I'm just leaving this on for a couple more minutes and check. I of course need to have more cooling capacity on this, but as it is now, it's about 50 degrees on the transistors, and it's down on 19 volt. 19 volt. Or 19 millivolt, as a person who would know what he's talking about should say. I is U over R, and it's 0.019. That's 19 millivolts divided by 0.22. About 86 So about 86 millivolts, probably enough, at least enough for us to get testing. And if we get the other one adjusted the same, we are ready to put in some audio signal on this and see what it does on the output. Also, a good test should be to measure how much DC bias you have on the output, and that is the differential voltage between 0 volt and the loudspeaker output. And we can measure that also, but before I take the measurement leads off, I'm going to switch this off, so I'm not short-circuiting anything. Wait till the voltage has dropped to a good level. 0 voltage drop over this. I can loosen this one. And I'm going to connect this to ground. This should be a good place to get ground. I can get this to stick. Okay, otherwise I can of course just measure here. This should also be a good place to find ground. Like so. Did I measure this wrong now? Did I have this on AC when I measured this last time after it was into... Do I have to do this again? I probably have to. Yeah, I just noticed that my multimeter was reading AC here. I had not turned this on the last time after this went into hibernation mode. I'm going to turn this up again. Yeah, but it doesn't matter much, it's measuring correct anyway, so I don't think it mattered that much. I'm going to turn it off again, and when this is down to 0 again, I'm going to disconnect. Zero volt. Like so, and this one over here. You can see now it's, yeah, then it's off. And the fuse was blowing. The fuse just went kaboom on me, totally black. And did I do anything wrong? I don't think so. This is from the speaker output to ground, and this is a multimeter. It should have plenty. Yeah, it should have very high impedance, so it shouldn't matter that much. Of course, it's AC when it's like so. DC. You can also see here on the capacitor, it's 280 millivolts, and it's 260 about millivolt here, so they're not that far away from each other. But that was a negative thing. I'm going to connect this up again as it was, like so. And I'm going to replace the fuse and see what happens. I have turned off the variac, but I have burned myself on broken fuses before, so I take no chances. I did remember that I put in quite a large fuse. Yeah, 0.5, a slow burning fuse. But hang on for a moment, I almost had myself confused here for a bit. And what did confuse me was that I thought that 0.52 amp fuse was a big fuse, but it certainly is not. If you take and make a dead short on this, and this is just an oversimplification, you know, because the output of this is not linear, but 120 volt amps over 230 volt is about 0.5 amps. And of course, a capacitor, when it's starting to charge, is almost a dead short. So I had already determined that this fuse here should be 1 amp. So I'm not sure what I was thinking here, but Clearly this fuse is too low, and why it didn't blow before, I'm not totally sure, but you do have some additional capacitors on this PCB, and I have not turned this on so many times with the amplifier connected. So surely the problem is that we have to upgrade to a bigger fuse. And when we connect both the boards together, that has to be done anyway. So I'm just going to real quick fix up the other board, and I'm going to try to connect them both together and then see what happens. Yeah, since I lost the footage when I did this the first time, I'm going to bother you with this when I do the other module, and it's just mounting the distance pieces. It's just adapting the silicone pads, mounting the silicone pads, and fastening the screws to get it onto the heat sink. So it's going to be done real fast. Yeah, just getting my gear set up here, and it's about connecting like we did last time, but this time I'm going to have both modules connected to power at the same time, but I'm going to change my specially made measurement bias measurement leads connected to the other module, and I'm going to try to hook everything up at once on power. The wires I have here on the power supply, they are kind of stiff and difficult to handle. It doesn't matter when I mount everything in a box, but as of now I should have had some silicone braided wires that was much easier to bend and handle when everything is just not fastened down as it is now. And as I told you before, there is always one, and this time it was the spade connector under the negative power connector that was not soldered. So I've looked at this numerous times, but I didn't notice until I tried to put the wire on and I felt that it was loose. Luckily, my Pinesil soldering iron is really up to the task. It's quick and fast and it's easy to get a hold of, and it's just a dream to work with. Yeah, now this feels really normal, so now I'm getting the negative power wire placed, and I'm also going to short out the input to get a good measurement and have no noise on the input that can disturb the measurements on the BIOS. And I'm going to use a spade connector that I have, not spade, but this it's this cable shoe really that fits into both this, and I'm just going to fasten that in the clamp to short the input. Yeah, just like so. And then it was the fuse, and we are not going to use the 0.5 amp fuse anymore. I'm going to put in a 1 amp fuse, so we won't blow this if I turn on the power without ramping it up slowly with the variac transformer. Yeah, I discovered that my Røde microphones, they was giving this metallic sound, and I'm not sure why that is. So I'm trying now with another microphone, and I'm just connecting up all my measurement leads and make sure that they are safely connected without shorting out anything, and that it will stay in place during the measurements that we need to take to figure this out. And as last time, I'm using my old Metex as the multimeter to measure the input voltage, It also has a low battery sign, so it's probably not totally accurate, but it's good enough for measuring the input voltage so that I will see if the variac is delivering what it should. And the other multimeter, the Fluke, is connected, and this time I remember to put it on DC. So it will be the same setup as last time on the other module, so the result will be comparable. Yeah, and now we are getting kind of a skewed view of the world. I knocked my camera off balance, and I really didn't notice when I was filming this, but we will get a close enough overview of what's happening on screen. I will adjust this to about 21 millivolts, and that will be something slightly below 100 milliamps. And of course we know that this is drifting, so it will lower with time. But at least when we have this bias current, we are not making this run away with heat, so that we will keep the circuit safe with the heat sink we have. And of course the drifting current is not a good thing, but just to make a sound test, that is quite good enough. And for those who wondered, I had turned the power off, and now I'm just connecting the leads up to the other module just to make the same measurements on that one. And of course it is now cooler than it was, so it will have a higher voltage than we measured last time. Yeah, and as you can see, it's almost 30 millivolts. And 30 millivolts, we know it's 136 milliamps. But then again, it will heat up faster and it will drop faster. So we are adjusting it to about the same as the other one was. Yeah, I'm turning off the power. I'm going to change out the measurement leads so that I can make a measurement on both of this in a safe way, so that I will be able to see that the modules are about the same when they have the same temperature. Yeah, and now they are about the same, but I do see that I should not have cut the heatsink in two different pieces, because if this has been thermally connected together, it will be easier to maintain the same temperature and the same temperature drift over both modules. But that will change when we mount them in the box. Yes, here you can see my setup, how I'm filming this. This is my what should I said? I'll turn off this so I don't get all the false light in from the side. My real life environment here, and I'm just going to show you some things here. Now the circuit, it's finished. It's almost ready to go live, I would say. But I was just making this, and this one. This is a signal lead that I was going to test it, but it's not working. So I have to get another 3.5 millimeter jack, and I can't do that until my son is back, and he's out at work today. So I'm not going to test this amplifier with audio today, but it's it's finished. It's ready to test, and I do have this with a cold adjustment for 86 something, 80, 90 milliamps, and that is enough to get decent sound, I will think. And I will have to do some measurements to see how the crossover is, but I need a good both signal source and a scope to watch how this looks in real life. And yeah, the circuit seems to be working. It lets itself calibrate. The aluminium heat sinks are a bit light, but this will do for testing if I don't increase the bias current, not voltage, sorry. But I think I will wrap this one up, and I will test with a signal as soon as possible. Hopefully it will be during this week. I will just get a short video. I will try to hook up some amplifiers and a signal source, and I will try to play some music on this one when I've tested with the first sinus wave to see that, yeah, that the signal, both halves, is looking okay-ish. So that's it for this episode. I did have some drawback. This blowing fuse made me confused wordplay, and I'm happy that this didn't throw me off track. But yeah, see you in the next time, and thanks. See you in the next one, and thanks for watching.